You're watching a Channel 98 NBISD TV production.
Oh, hello there again. Welcome to Deja Vu. It's Algebra 2. I'm your host, Kevin Corpy. Just working on another one of those algebra problems there. Today we got a great show for you. We're going to be solving equations. Now, as you remember from the first show, hopefully you still remember, one of the main reasons for studying algebra throughout the ages is to solve problems. We develop algebraic models to model real-life phenomena. And then once we get the equation that models the phenomena, it comes down to solving the equations. And the solutions to the problems in the real world come down to finding the solutions to those equations that model the behavior. Now, if we are fortunate enough to be working with equations that deal in one variable, unlike Diophantine equations, remember, then it makes the calculations all that much more easy. Well, on today's show, we're going to be looking at specific special types of those equations in one variable, namely x to the first power, or linear equations. Now, if that doesn't excite you and keep you glued to the set, I don't know what will. So why don't you go download those worksheets from the website, www.newbraunfels.txed.net, and I'll wait for you very shortly to return because we're going to do some math today on the program. All right, lesson 3 already, 3 episodes into the season, and we're solving linear equations. Okay, very important stuff. And before we start, it's even more important that we understand the terminology that I'm going to be using on the show, because you're not going to be able to understand the equations if you don't understand what makes up the equation. So let's review here. We've got variables in algebra. Variables are the unknown quantities in an equation or in an expression that are usually represented by a single letter. Remember, this was the full symbolic algebra that evolved from the rhetorical algebra. Some of the most famous, we can call them, letters that are used are, of course, x, solving for x. We'll see y quite a bit. Occasionally a z shows up, and when we're doing applications, the letter t for time will arise. We can use the set u or v, and a and b show up as common letters. When we're talking about numbers, we've already seen n this year. If we're ever talking about angles, the Greek letter theta will magically appear, and sometimes to denote other angles we use alpha, the Greek alpha, or the Greek beta. So that's just a sampling of some of the variables or the letters that we're going to use to represent unknown quantities throughout the year. Now, important, in class I see students mistaking these quite a bit. The difference between a term and a factor, a huge difference, okay? So here's what a term is. A term is a variable or variables or numbers that are added or subtracted to each other. That means they're separated by a plus sign or a minus sign. For example, in this expression, 3 plus x, there are 2 terms. The 3 is a term, the x is a term. They are separated by a plus sign, okay, terms. In this expression, 5x minus 7x squared, I again have 2 terms. There's one minus sign separating these 2 terms. The 5x is a single term, and the 7x squared is the other term. If I added on back here, minus an x squared plus 1 quantity, that's grouped in these parentheses, this would be 2 minus signs that are separating 1, 2, 3 quantities. So this whole thing right here, x squared plus 1, would be its own term. Now notice that inside there, it has 2 terms of itself, but because of the grouping symbol, we treat the whole thing as one term. All right, so terms, plus or minus. Factors. Factors are variables or numbers that are either multiplied or divided in each term. That means they're separated by multiplication symbols. And we don't use the x anymore for multiplication because we confuse it with x. So we typically use parentheses, or we can use a little dot, or if it's a number followed by a variable, we can just write them side by side like that, like 3x. But of course, if we wanted to do 3 by 3, writing them side by side wouldn't work because we think that's 33. So we'd want to put that in parentheses or put a dot in between them. All right, now factors are important. Let's look at some examples. If I have this expression, 5x squared y, that's one term. There's no plus or minuses, but it has 1, 2, 3 distinct factors, the 5, the x squared, and the y. they're all multiplied together. Some might even consider the x squared as being 2 factors. But notice there's no plus or minus signs. So one term, 3 factors. If I look at something like this, 8x minus 2x squared, I have 2 terms, and in the first term I have 1, 2 factors, and in the second term I have 1, 2 factors. So what would some look like if they're divided? Well, if I had 3x squared divided by 5y, notice that in the numerator I have 3 times x squared divided by 5 times y. This is a single term with 1, 2, 3, 4 factors. All right, so terms and factors, got those down. Now what I've been calling all these things up here are algebraic expressions. So what an algebraic expression is it's a collection of factors or terms containing variables or numbers. That's it. Expressions do not contain an equal sign. So everything up here is an expression, okay? It's like a fragment of an equation. Now here's why it's important to understand algebraic expressions. If I ask some students in class to simplify this expression, 1 over the square root of x, many of them, out of reflex, want to get rid of the radical, which is good. But what they do is they square the numerator and they square the denominator. Well, that will accomplish the goal of getting rid of the radical in the denominator, but we can't do that. These are actually not equivalent, because when you square an expression, like the number 5, you change its value. So it would become a 25. So in general, all you can do to algebraic expressions to modify them is to multiply by clever forms of 1 or to add a clever form of 0. But you have to know what that clever form is for it to be in any use. So algebraic expressions don't have an equal sign. All right. That brings us to an equation. An equation now is a mathematical sentence stating that 2 expressions are equivalent. The expressions are connected, of course, by the equal sign. So if I take any 2 expressions, like the expression 5 times x minus 7, that's an expression, single term with 1, 2 factors. This entire quantity in grouping symbols is a factor. And I take the expression 25. Okay? If I then set them equal to each other, I now have an equation. And this is, in fact, a linear equation, which we're going to talk about solving today. All right? So an equation now, you can square the expression on the left-hand side so long as you square it on the right-hand side. And we'll talk about why that works for an equation and not an expression here in just a little bit. Now, the whole point of this is to solve these equations. And we're going to be looking at solutions today, and sometimes later on we're going to be looking at sets of solutions. So here's what a solution set is to an equation. It's the set of values, or the value, it could be just one, of the variable in an equation that make the equation a true statement. For example, in this equation, 2x equals 6. Can you think of a number that when you multiply by 2 will equal 6? Well, yes, the answer is x equals 3. So 3 is the only solution to this. We can actually write 3 in a set notation. We can say that the solution is the set that contains 3, and we can write it just like that. Remember, these braces denote a set. Or if you want to get really fancy, you could say the solution set is the set of all x such that x equals 3. And that's called set builder notation. It has one element. The cardinality of the set is 1. We would call this a conditional equation because it is a true statement only under the condition that x is 3. One solution. All right, now, today we're talking about linear equations in one variable. We're going to have just one variable, whether it's an x or a t or whatever. And it can be written, any linear equation can be written in this form right here. Now, I know you're looking at it and you're saying, hey, Mr. Corpy, that looks like 3 variables to me, right? It looks like an a, an x, and a b. Well, correct. There's 3 letters there, but in a linear equation, we are going to be treating a and b as constants. We can write that mathematically as a comma b epsilon, which means are elements of the set of real numbers. And we have to make one qualification on a. A can't be 0, because if a is 0, the x term goes away. And it's very important for our linear equations to have an x term. X then is our variable. A and b are going to be numbers. Let me show you what I mean. Here's some examples. What is linear? What is not as linear? Linear, for example, 4x equals 8. That's a linear equation. I can subtract 8 from both sides and make it look like 4x plus a negative 8 equals 0. The important thing to notice about the linear equation, though, is that the exponent on the x is an implied 1. Very important for linear equations, that the exponent on the x is a 1. Okay? Let's look at this one. It's 3x minus 2/3 x equals -9. The exponent on both x's, although it's in two places, it's still a 1. We would call these like terms, and we can combine them. And when we combine them, we're going to get one new number times x to the first. So that would still be linear. We don't necessarily have to get it to look like this to decide if it's linear. All right, let's move down. This one here, 2x minus 5 equals 1/10, or 0.1x plus 2. That's an x to the first and an x to the first. And when I combine x's on one side, it's still going to be written as x to the first. Now I'm switching variables on you down here. Now I've got a t, but notice that if I did distribute this too, it would still be t to the first plus t to the first. And over here, it's not in blue, but it should be, it's a t to the first. This is the square root of 3 times t, where t is outside the radical. So all my t's in here are to the first power. That's important. We call those degree 1. Degree 1 equations are linear. The degree is just the largest exponent on any variable term. And when they're all 1s, we say it's linear. Let's look at some nonlinears. Nonlinears. In this one right here, we've got to be careful, because if we look at the x, it appears that it's an implied 1. But notice where the x lives. The x lives under the radical, which, as you'll see later on in the year, is equivalent to x to the 1/2. Well, 1/2 is not equal to 1. So this would be a nonlinear. This is actually a radical equation. We'll talk about those later. Next example, we got 2 over x equals 41. Again, you got to be careful, because just casual inspection, you see an implied 1 exponent on the x. But notice that it lives in the denominator, not in the numerator. So if I was to rewrite this later on in the year, an x in the denominator is the same as an x to the negative first in the numerator. And so that is not linear. That's not a 1. That's the opposite of 1. Here's another case, 3 minus 2 raised to the x power. Well, again, it looks like the exponent on the x is a 1, and it is. But x is not our variable on the ground floor anymore. X is in the exponent. And so this would be an exponential equation, not a linear. And then finally down here, we got to be really careful. This one fails for 2 reasons. We look like we have t's to the first power everywhere. But if you notice on this one, if I went ahead and distributed here, I get 2t times t, which is 2t to the second power. And so that makes it nonlinear. Also over here, I've extended this radical out beyond the t. So again, this t now being under the radical makes it essentially a t to the 1/2. So this is by far a linear equation, far from being linear. So now that we have linear equations, how do we go about solving them systematically? Well, it's like a recipe, okay? We need to establish a systematic algorithm that will allow us to isolate the variable on one side and our coveted value on the other. I mean, our goal, if a variable is x, is to get down to x equals some number. And that's basically a sentence declaring what the solution set is, or what the solution is. Now, because we're working with equations, there are some things that we can do that are legal, that do not change the value or the values of the solutions, and some operations that are illegal. So here's a nice analogy for an equation. I'm sure many of you that have had an algebra class have seen this analogy before. Think of an equation as a set of balanced scales, and the middle right here is our equal sign. So let's say we're starting with 2x equals 4. What can we do to both sides? Well, whatever we do to one side, in order to keep the scales balanced, we have to do it to the other side. So if I add 7 to this side, the left side, I got to add 7 to the right side so it balances out. So we can add a number to both sides. That's legal. What if I want to multiply or divide? Well, if I multiply by 3 or divide by 2, or multiply by 3/2 to one side, I got to multiply the other side by the same number. So multiplication and division is okay. What else can I do? Well, I can subtract variables or numbers. So I can subtract an x from this side, and if I do, I got to subtract an x from that side. So long as we're keeping this operation balanced, we're not changing the value of the solutions. It's a good time to take a break to watch some valuable public service announcements. But as you're gone, ponder this. Why did the Romans have so much trouble with algebra? The answer when you get back.
There comes a point in your life when you realize you're not a kid anymore. Suddenly, you have to make decisions. You have to make choices every day. This is the time when you define yourself, or you let others define you. You quickly learn that there are 2 ways to go: under the influence or above the influence. I am above the influence.
Dad, are shiny and round. Nickels are also round. Dollars are not round. Dollars are rectangles. What can I buy with 2 rectangles?
A bus ride.
You're right. Good job, honey.
When you talk with your child, you build vocabulary, and learning starts long before school does. For more tips, go to bornlearning.org.
Welcome back to Deja Vu. It's Algebra 2. As always, I'm your host, Kevin Corpy. Hope you enjoyed those PSAs. Have you thought about the answer to that question? Why did the Romans have so much trouble with algebra? Well, it's because to them, x was always 10. All right, so I said solving equations is like a recipe. So what's your recipe for solving equations? Well, here it is. I've made you a nice little recipe card. Download it, cut it out, and use it over and over and over again. Share it with your friends, okay? Here's your recipe to solve linear equations. Number 1, expand out the equation. And what does that mean? That means if you have anything raised to a higher power, go ahead and use FOIL if you must, but you're basically expanding out terms. If there's anything to distribute, you want to distribute it to all the terms. Once you have the equation entirely expanded on both sides, your next step would be to collect your like terms. And what I mean by like terms, variables on one side, I prefer the left, and numbers without variables on the right-hand side. That's what I prefer. You can actually collect them on either side, but you do want to separate them on either side of the equation. And once you have your like terms collected, all you have to do then is solve for the indicated variable, which is going to be pretty easy. And then when you're done with this little recipe for best results, you're going to let your equation stand for 1 minute afterwards so that you can marvel at your work. And then you reuse the recipe over and over again to solve other equations. Pretty cool, huh? All right, let's try out this recipe and see what kind of tasty equations we can come up with. Here's one right here. 4 times the quantity m plus 12 equals negative 36. It is a linear equation. It's a linear equation in terms of m. But that's okay. One variable and the exponent on m is 1, so it is linear. Well, by the recipe, we need to expand out the equation. And so we would distribute this 4 to both terms inside the parentheses. And that gives me a 4m plus 4 times 12 is 48 equals negative 36. All right, we've expanded it out. I've got one variable term here, and I've got 2 constants. So I'm going to subtract 48 from both sides. Okay, subtract 48 from the left. I got to subtract 48 from the right. Now, that's the actual process of what we're doing there. But what I'm going to start doing on this show, since it is Algebra 2, is I'm going to actually be bringing it across and changing the sign. That's a trick, that's a gimmick, but it works because we are actually subtracting from both sides. So that leaves me 4m plus 0, or just 4m. And over here, negative 36 minus 48 is going to be negative 84. So there we go. We've got 4m's on this side and negative 84 constants on the other. To solve for m now, all we have to do is do the inverse operation over here. This says 4 times n. And so we want to undo multiplying by 4, and that operation is division. So the inverse operation of multiplying by 4 is dividing by 4. And so if I do it to one side, I have to divide it on the other. And your 4's will divide out. And here's what's important about factors. If this was 4 plus m, and let me come off to the side here. If that was 4 plus m over 4, here's a common mistake that I see students make. They want to divide these out. That is a no-no. No-no. We can only divide out common factors. And factors are multiplied. In the numerator here, 4 was a term, not a factor. But over here, it's 4 times m divided by 4. So they do divide out, and I get m equals negative 84 fourths, which is negative 21. So negative 21 is the solution. So you can write your answer as m equals negative 21. Your teacher might accept that. Or you get fancy and write it in your set notation, or the set of all m such that m equals negative 21. That's really fancy. All right, simple linear equation. Now some of y'all might be looking at this a little bit differently, and there is another way to solve this. So what do good cooks or good bakers do? They bake a lot using the same recipe, and then they start to add their own ingredients, and they tweak the recipes a little bit. Well, once you work enough equations, you can see things a little bit differently, and you can modify the recipe. Because 36 and 4 goes into 36 evenly, it's a factor of 36, some of y'all might have preferred to divide by 4 from the onset. And if you do that, you get m plus 12 equals negative 9. And what does that do? That just keeps the numbers down a little bit, keeps them smaller, and then you subtract 12 from both sides, and you get m equals negative 9 minus 12 is the same answer, negative 21. So the recipe definitely works, but feel free to tweak it a little bit if you need to. The key is to not break any algebraic rules. Whatever you do to one side, you have to do to the other. All right, let's look at another example. This is a linear equation in terms of my favorite variable, k. I wonder why. Let's see. I've got k to the first, and I got a k over here. So let's go ahead and expand this out. While I'm expanding it out, there's no reason why I can't combine like terms as I go to kind of save a little bit of writing. So what will I get here? I get 3k minus 14k is negative 11k plus 25. If I distribute here, I get 2 minus 6k minus 12, distributing the 2 to all the factors. So I've got an 11k over here and a 6k over there. I like to underline like factors. So I'm just going to bring the 6 across and change its sign. It's like adding 6 to both sides, 6k. So negative 11k plus 6k. And on the right-hand side, I've got a 2 minus 12. Well, that's going to be a negative 10. And then I still have this number on the left-hand side that I need to subtract, and it becomes a negative 25 on the right-hand side. Now what I can do is I can collect these like terms. Negative 11 plus 6 is negative 5k, and negative 10 minus 25 is negative 35. So now I've combined all my like terms, and it's time to divide by negative 5, both sides. Negative divided by negative is positive, and so on this side I get k equals 7. And again, if you want to write it in set builder notation, that's okay. And there's your answer. Now what you could do always, remember, is you could plug 7 back into the original equation on both sides, and you should get a true statement. Okay? That is a good habit to get into. But sometimes you might feel so confident with your work the first time, or time might be an issue. You don't have time to go back and check every answer. You can build up your confidence and know that your answer at the end is going to be correct. But you got to watch out for careless mistakes, like missing a distribution or something. Okay? Here's another example. This one looks a little bit different. It's a linear equation. We have p's now as our variable, and both of their exponents are a 1. This is actually a special type of equation where you have a ratio or a fraction equaling another ratio or a single fraction. This is called a proportion. And we looked at proportions quite a bit on last year's geometry show. We saw proportions on that show algebraically, and the tried and true method for solving proportions is to find the cross products or cross multiply. And it doesn't matter which way you cross multiply as long as you multiply across the diagonal. I prefer to start in the top left. So if I multiply, I'm going to get negative 2 times the quantity p minus 3. Now notice I'm not trying to multiply the negative 2 times both of those. In other words, I'm not distributing in my head. The more you try to do in your head, the more likely you're going to make a careless mistake. So go ahead and just write it down. Negative 2 times the quantity p minus 3 equals 8 times its cross product, p plus 5. Now you've got it kind of without the fractions. It's on the ground floor. Now you can expand it out. If you wanted to, you could divide by negative 2. I'm not going to do that. If you want to try it at home, go ahead and see if you get the same answer. I'm going to distribute. So I get negative 2p plus 6 equals 8p plus, and this is actually a 5, so 5 times 8 is 40. So there's my p's that I need to get together, and here's my numbers. So variables on the left, so negative p, I have to subtract the 8p. And numbers on the right, the 40 is already over there on the right, and he is welcoming with open arms the number 6, although we have to change its sign. So now I combine these, and I get negative 10p equals 40 minus 6, which is 34. And I can sense the end here. We're getting close. We divide both sides by negative 10, and we get the answer to be negative 34 tenths. Well, that's a nice rational number, but it does simplify. It has a common factor at least of a 2. So if I factor a 2 out, and here's common factors. If you want to write it like this, it's negative 2 times 17 and 2 times 5. What we're essentially doing when we simplify fractions is we're dividing out the common factors. And so an equivalent version would be negative 17 fifths. And I prefer to put my answers in simplified rational form, although some of y'all might come over here and say that's the same as negative 3.4. And you'd be right. Most people who think in terms of decimals are probably accustomed to resorting to their calculator out of a reflex. And I would discourage you from doing that. Try to do as much in your head and try to write your answers as a simplified fraction. Or do what your teacher prefers. That's a good thing to do as well. Now it's time for the program called Deja Review. All right, so we're going to look at two special types of linear equations today. The first type we're going to call type 1. Very appropriate name. The second type, yep, type 2. All right, so let's look at type 1. The variable is v. 3v minus 9 minus 4v equals negative 5, or the quantity 5 plus v. So yes, it is linear. I've got 3 v's, and they're all to the first power. So it is a linear equation. So let's go ahead and use the prescription. There's really nothing to expand on the left side, but I can already combine the two like terms that are there. 3v minus 4v is negative v minus 9 equals distributing the negative. That's a negative 5 minus v. Well, here's my v's that I got to get together. So I'm going to keep them on the left. So this negative v stays. He welcomes this guy over. By adding v to both sides, we get a positive v. So the negative 5 stays on the right. He's the placeholder on the right-hand side for the numbers. By adding 9 to both sides, bringing him across, changing his sign, we get that. So what happens here? I get negative v plus v. Remember, v is a variable. So this could be negative 5 plus 5, negative 10 plus 10. These are going to be opposites of each other, and those make a zero pair. They will always cancel. Very curious. And over here I get 9 minus 5. Well, that's 4. So we get down to this right here. We get down to the statement or the equation that 0 equals 4. Well, you're sitting at home going, what? 0 does not equal 4, Mr. Corpy. And you are right. It does not equal 4. Notice also that our variables mysteriously vanished from the equation. And we ended up with a clearly untrue statement. Now what that means is it doesn't matter what value of v you plug in to the original equation on both sides. It will always get to this point where whatever number you plugged in will cancel out and you'll get an untrue statement. We call this type of equation a contradiction. 0 does not equal 4. And contradictions have no solutions. You can try all you want by trial and error. Plug in as many different values of v as you want that are numbers, and you're always going to get an untrue statement. None of them work. How do we express no solutions in set form? Well, you can say that it's the set of nothing, which we call this the empty set. Or there's another way. You can equivalently write it as a circle with a backslash through it, and we read that as the null set. They typically mean the same thing. It just means no solution. Now, what you don't want to do, this is a no-no, big-time no-no. You don't want to, just to cover all the bases here, you don't want to say that it's the set that includes the null set. Because believe it or not, mathematically, this is not an empty set. This is a set that contains the empty set. So it's not empty. It's like putting an empty coffee can, the null set, inside another coffee can. They're both empty, but one coffee can is inside the other. So don't do that. Use one or the other. Okay? Pretty cool. That math notation. Don't get hung up on it. All right. Type 2 is a linear equation. We've got x, x, x. And let's go ahead and use our recipe. We'll expand it out. 2x minus 12 equals, now I can combine like terms, and I like to do that as I go from one line to the next. Negative 5x plus 7x is 2x minus 12. And you're probably already recognizing something. I've got 2x minus 12 equals 2x minus 12. Well, yeah, that's a true statement. What's going to happen if we keep going? Well, let's see. I will collect my variables on the left. So this 2x is here. Subtracting, I get minus 2x. And I'm going to keep the negative 12 on the right-hand side and bring this negative 12 across, and it becomes positive. Now look at this fascinating conclusion. 2x minus 2x, that's absolutely nothing. Negative 12 plus 12, that's absolutely nothing. Aha! That's better than before. Our variables disappeared again, but unlike before where I got an untrue statement, I get a true statement. This right here is called an identity. And unlike a contradiction that had no solutions, an identity is true for all x in the domain. In this case, it's all real numbers. In other words, it doesn't matter what value of x you plug into the original equation, you are always going to get a true statement. Try any number at home. Try 1, try 5, try a negative 52 million.3 if you want to challenge yourself. You're going to get a true statement out here at the end. So we've got conditional equations, like the ones we worked at the beginning, where there's only one solution. We've got contradictions, where there's no solutions. And now we have identities, where there's infinitely many solutions. Infinity. So there you have it, solving linear equations. Some today were more difficult than others, but regardless of the level of sophistication, you only get good by working many, many, many problems in a lot of different varieties. And that's the key. Practice, practice, practice. The more you practice, the better you get. And the better you get, the more likely you are to see the little subtle nuances of each problem, which might actually make you more efficient in solving these equations. But first, before efficiency, comes effectiveness. So you have to be effective before you become efficient. Practice. Okay? Until next time, I am Kevin Corpy, and I'm reminding you to do your homework.